Reason that we're talking about inverses of exponential functions is exponential log functions are inverses of exponential functions. Okay? So here we go. Exponential functions, if you remember, and this is a good review, an exponential function passes through 1, doesn't it? And it goes close to, it never crosses the x-axis, and then it grows like this, doesn't it? Now, if something is an inverse of something else, you'll remember from when we did this that it is the reflection across the line y equals x, okay? So if we take this guy and we reflect it across that, you remember they ended up looking a little bit like a butterfly, then 0, 1, this is the point 0, 1, then becomes the point 1, 0, doesn't it? So if this doesn't cross the x-axis, then this guy doesn't cross the y-axis. He actually ends up going this way. Remember how they look like reflections of each other across that line? So, guys, this is y equals b to the x power. This guy right here is y equals log base b of x. That's how we say that. They are inverses. Okay? Now, we need to go and remember how to go back and forth between those two things. It's an easy way to do it. Did you know that you can swap between an exponential and a log function? Let me show you how you do it. You have y equals b to the x. Normally, we don't solve a log function. Normally, we solve an exponential. Okay? Now, how we do it is as follows. We go around the world. We curly Q. Okay? We say log base b. So we go b log base b of y equals x. So we start here and we spiral around. We spiral. Okay? The same spiral works if you have log and you're trying to put it into an exponential. Watch. Start in the middle. B to the x equals y. So in both cases, we're starting at the b, spiraling across the equal sign, and then coming back. Do you see the spiral? I hope so.
Wait, so why do we have to do that?
You'll see.
It's like the BAE, like the base thing that this one uses. Yeah.
Now, here's why. Take a look at log base 2 of 8 equals 3. Remember the spiral I just talked about? 2 to the, rewrite that. 2 to the what? Third power equals what? So they're equivalent, that's why. We can solve 2 to the third power, can't we? You don't know how to solve log base 2 of 8. So we turn log functions into exponentials to help solve them. Make sense? Take a look. 3 to the what? 3 is the base in both places, isn't it? So 3 to what power? So the 1/2 power is equal to what? Isn't the 1/2 power the same as the square root? So it's true. Okay? See if you can turn C into something. Rewrite C. What's the base in C? 5. 5 to what power? The negative 2 equals what? 1 over 25, doesn't it? And it does, doesn't it? Because doesn't 5 to the negative 2, isn't that the same as 1 over 5 to the second power? Because it drops it down, and 5 to the second power is 25. So now, what about log 7 of 7? If these two numbers match, guess what this is always going to be? It's always going to be 1. Think about why that is. 7 to what power? Equals. So something to the first power is always equal to itself, isn't it? So if these two numbers are the same, the answer is always 1.
So it's just 1.
It's just 1, yeah. Now let's look. Look what I'm showing you. Log base b of 1. Any log of 1 is equal to what? Think about why that is. B to the what? B to the 0 power. And what is anything to the 0 power? 1. So anything, log base anything of 1 is 0. That's a property. Notice that's log base b of b. We just did that one, didn't we? Is 1. Log base b of b to the y is y, isn't it? Think about why that is. Log base b of b, we said was, yeah, b to the y power is, sure enough, b to the y power, isn't it? So I want you to look and see how this helps you. If we have log base b of something to a power, we can just get rid of it. Same thing happens here with e. Natural log and e are the same. Natural log, by the way, natural log is log base e. That would be log base e of e to the y. And didn't we say, so now doesn't this match this? Yes? So doesn't it make sense that log base e of e goes away? So e and natural log, look at this one. This one's one you need to know. I want you to look at b to the log base b. If we have b to the log base b of x, look what happens to the b log base b. It's like it disappears, doesn't it? And just whatever's here comes down. Same with this. E and natural log cancel each other out. Yes?
It would just be like x equals x.
Yeah, which is true, isn't it? But the big thing is b log base b cancels out. E natural log cancels out. Cancels out the other way too. Look, ln e, didn't we say canceled out? So natural log and e cancel out, and e to the natural log cancels out. Just like it does here. That cancels out, and all that's left would be 1. Yes?
Do the b's and the b's have to be the same?
Yes.
What if they're not?
Then they don't cancel out.
Then how would you do that? How would you rewrite that?
That would be a much harder problem that I'm not going to give you. That's a higher level. That's like a calculus thing. But look at this guy. 6, log base 6. What did we say about 6, log base 6? What happens to those two things? 6 and log base 6, they cancel. So what would be left would be 11. Told you this is an easy lesson. So far, so good, right? Previous page. What did that property say log base b of b was? 1. So doesn't the log equation look like, if you look at this, what did that log function look like this, didn't it? This log function doesn't go into the negative numbers, does it? So do you see why a log, you cannot take the log of a negative number? It's automatically. All right, so now, let's look at these guys. Log functions are inverses of exponential functions. So how we do this is we plug in to the log function and then we flip the coordinates. What is 2? If x is negative 2, wouldn't this be 2 to the negative 2? What is 2 to the negative 2 going to be? 1 over 4. It'd be the same as 1 over 2 squared, wouldn't it? Which is 1/4. So -2, 1/4. And remember, we said these are inverses, didn't we? And what do inverses mean? The x and the y are. So if we have log base 2 of x, instead of -2, 1/4, we now have 1/4. -2 is our xy coordinate pair. Make sense? So we can use the exponential function to graph the log function by finding the exponential function, because that's easy to do, and then flipping the coordinates. What if we do 2 to the -1? What's it going to be? 1/2.
Wait, so how'd you get -2 over there?
Oh, because the x is -2 and the y is 1/4. And what did we say we do with the x and the y for an inverse? We swap them. So this x and this y, remember this is a y, so this x and y became, they swapped. My x, this was my coordinate pair to begin with, -2, 1/4. So to do the inverse, I simply swap those two around. So instead of -2, 1/4, I got 1/4, -2. Okay? So the same thing here. So now I have -1, 1/2. So what is my new coordinate pair for the inverse going to be? Yeah. So that's how I would graph this guy. So what would 2 to the 0 be? 1. So my coordinate pair is 0, 1 for this guy. So what's my coordinate pair for its inverse going to be? 1, 0. 2 to the first. Try 2 to the first and 2 to the second and see if you can find the two last remaining coordinate pairs. What's 2 to the first? So what's the new coordinate pair for the inverse? 2, 1, right? 2 squared? So the new, yeah, 4, 2. Yeah, that's what I'm saying. They just flip. If you got an inverse, the x becomes the y becomes the x. They just switch. That's what this means. The x and y are switched for an inverse. Common logs. Common logs are base 10. Guys, this is our number system. We are a common log base 10 system. Think about it. Every time you move the decimal, it's a power of 10, isn't it? So we are a base 10 system. If the way we know it's base 10 is we don't put the subscript base in there. So if you see log 100, what it's really saying is log base 10 of 100. Okay? Now, we want to turn this into, this is how we solve. We want to turn this into, and we want to solve and figure out what this is. The way we do that is we stick an X out here, and then we do our spiral and turn it into an exponential. So how would I rewrite this as an exponential? What's the base? 10 to the what? 10 to the X is equal to what? 100. Now, to solve this, we need the same base. Can we write 100 as a power of 10? 100 is 10 to what power? The second power, isn't it? Yes? Not 10 times 10. 10 squared, right? You got to think powers, not multiples. So, if 10 to the x is equal to 10 to the second, I want you to notice something. We can get rid of this part because it matches. So what does x equal? Yes, so x equals 2. Let's try it again. Is anybody confused? We're going to turn it, well, let's look at a couple more and see if we can get them. This is log base 10, isn't it? You know, I know that because it just says log.
Right.
There's no number down there, is there?
Isn't it always a 10 if there's no?
Yep.
Yeah, I remember that.
So we're going to rewrite log base 10 of the square root of 10 equals, we don't know, do we? So what do we call it if we don't know? X. Now we're going to use our spiral and rewrite it. Use your spiral. So this becomes 10 to the what? 10 to the x. Now we need to rewrite that as a base 10. How do we rewrite square root as an exponent? 10 to the what power? We just did this earlier. No, 10 squared is 100. What? 1/2. Yes, thank you. It's 1/2. Square root is the same as power of 1/2. Okay? If you don't remember that, make sure you make a note of that. Square root is 1/2. Cube root would be 1/3. Fifth root would be 1/5. So now what is x? Because the bases match, we can mark them out. So x equals what? 1/2. Right? You get,
Just put this in your calculator. There is a way.
there is a way, but I will give you part of this test without a calculator because you have to be able to do this. Now, try C. Let's try C. How do we rewrite it? Log base what? Log base 10 of 1 over 1,000 equals, now rewrite it, spiral and rewrite. Did you get 10 to the x equals 1 over 1,000, right? Okay, so now we got to get 1 over 1,000 to be base 10. So this is 1 over 10 to the what? The what? No, 10 times 100 is 1,000, but that's not multiplication. Exponent. 10 to what exponent is 1,000? To the third. So this is 1 over 10 to the third, but that's not good enough because that 1, it can't be 1 over. So how do we move it from the bottom to the top? Make what negative? The exponent negative, right? If it's in, remember your exponent rules from like algebra 1. If it's in the bottom, if it comes up, it becomes negative, doesn't it?
So it just be -3.
X equals -3, yes. Now, this last one is weird because it doesn't match, does it? But this is where we need to go back to those rules. What were our rules that we had? What did log base b of b equal? Look right here. This is log base b of b. Look on the previous page. What does log base b of b equal?
And then the 6 comes out.
No, because those don't match. This is the case where those don't match. Look at your properties. If you look at your properties, it means that we can now replace this with a what? And we put it equal to x, don't we? So what is 10 to the first power? It's just 10, isn't it? So what is x equal to? X is 10. Now, what if we have weird numbers? This is where you can pull out your calculator. If it is a weird number, now we can do this.
Wait, so the number C1, why did you do 1 to negative C1? What?
Because I knew 1,000 was a 10 to the some power.
But like, why'd you do it as a fraction?
Because it was a fraction here. 10 to the x equals 1 over 1,000.
Oh wait, I see.
Yeah.
Writing -3 is the same as 1/3.
It's not 1/3. I'm sorry, what are you asking?
Like, so you sell the powers, like 10 to the -3
1 over 10 to the third is the same as 10 to the negative third. Remember, the negative in the exponent simply moves its position in the fraction. Okay? A to the negative n is the same as 1 over a to the n, or vice versa. So if it's in the bottom, I can move it up by putting a negative in front of the exponent. If it's a negative in the top, I can move it down and get rid of the negative on the exponent. Okay? Log 34.5. Get your calculator out and look for the log button. There should be a button right down the first column that says log. That is your common log button. Hit that log and plug in 34.5.
Really?
Yeah, it really is that easy.
How many places does it replace?
3 decimal places. So you should get 1.538. And then do log 0.43. Now I want you to try log of -3. You're going to get a message. What did it say? Error. I want you to think about what the log equation looks like. Remember the log in mind. -3 is undefined. You cannot take the log of a negative number. So it says, can we make a general statement about log functions? Yeah. Logs are not defined for negative values of x. In other words, the domain is everything from 0 to infinity, isn't it? So now let's start solving some stuff. Let's see if you can solve a couple of these by rewriting them. So in A, what is the base? It's 10, isn't it? So the first thing we're going to do is rewrite this as log base what? Now spiral. How do we rewrite this when we spiral? 10 to the what? Equals. Ooh, this one's even easier. Do we have to do anything else but figure out what that is? You can do 10 to the third, can't you? Heck, we did that earlier. What is 10 to the third? Okay, so what is x equal to? So we can solve logs by turning them into exponentials. Look what it says. To solve a log equation, change it to an exponential equation. Do the same thing for B. Do your spiral and figure out what it is. Rewrite it and solve it. Check your answer. Did you get it? Good. See? You can do it. I told you this is an easy lesson, isn't it? Two to the fifth equals x, right? We can do these. Everybody good with this so far? Feel comfortable? What's 2 to the 5th power? It's not 10. Put it in your calculator. 2 raised to the 5th power. We'll do it on your hands. 2, 4, 8, 16, 32, right? Doubling each time. Just don't make the mistake of, here's the thing. If you've got a big number and a little number, you cannot multiply. You have to do powers. That's how I tell everybody. 2 big numbers you can multiply. Big number, little number, you cannot. Right? Numbers have to be the same size to multiply. It almost rhymes. All right. Remember what I said. Natural log x, ln x is the same. Ln is the same as writing log base e. Okay? Ln is the same as log base e. So that's what we do, is we rewrite the ln as log base e, and then we do our spiral. Okay? So try this. Ln is what? Log base e of the square root of e equals, if we want to solve this, what do? X. So now, can we do our spiral? What does the spiral tell us it's going to be? E to the x equals what? Square root of e. Now we have to rewrite that as a power. How do we rewrite square root? What is the power? E to the what? Square root is 1/2. Thank you. So this is e to the 1/2. So what does x equal? Yes. Now, some of them are even easier, because what did we say about natural log and e? What do they do to each other? They cancel, don't they? So if I have natural log e right here, I can just draw a line through it. So what is x equal to? Guys, what's left? So if this equals x, then x equals 5, right? Try C. Tell me what, if this is equal to x, tell me what x is equal to. What do we say about ln and e? Yeah, look on that first page of the properties. If we have e to the natural log, what happens to the e to the natural log? It does what? It cancels out, doesn't it? Boom, gone. So what is x equal to? These are easy. E and ln stuff where they're touching, easy. You just mark them out. And whatever's left comes out. Okay? How do we feel about that? Now, we don't have that here, do we? We could write this as log base. Now, you can do this one of 2 ways. You got an E button, but you also have a natural log button. Look below log. We call it natural log, but it's actually a French word, log natural. That's why it's ln instead of nl. Ln button is the natural log button on your calculator. Hit ln and plug in the number. What about B? And you shouldn't even have to plug in for C, because what are you seeing in there? A negative. Can we take the log base E, log base anything of a negative number? Nope. So this is negative number, so it is undefined. So now, very quickly, try example 7. Try A and B. You should be able to give me answers. If this is equal to x, what is x equal to? If this is equal to x, what is x equal to? If this is equal to x, what is this equal to? What is this equal to?
Just A and B.
Try A and B first. You should be able to get those just like boom. What's going to help me solve A? Canceling. Got ln right up next to e, don't we? If we have an ln next to an e, what happens to them? So what is x? What about b? ln and e next to each other, so x is. Now, this guy, we almost have the same, we do have the same thing. We got an e and an ln, don't we? So, what is this equal to? Square root of, can't we simplify that though? What is the square root of 9? So this would be 3 times the square root of x, wouldn't it? So if you can simplify, simplify. Now, we almost have an ln and an e next to each other here. We don't quite though, do we? Because that e is in the bottom. For the ln and the e to snug up to each other, it has to be right next to it. So how can I change this to make the e come up? Bring it up and the exponent becomes negative. So we can rewrite this as natural log of e to the what? All right. Now we have an ln and an e next to each other, don't we? No, this is not undefined. It would be if we were taking the natural log of -5, not e to the -5th. So x would be what? Yes. Okay? We're getting close. We get the last little bit here is graphing log functions. What is the basic natural log function of a graph? We did this already for a log function. We said it passed through what right here? What was that number? 1, wasn't it? This passes through the point 1. We know we had a vertical asymptote right here, didn't we? And what did the graph look like? It got really close here, and it grew this way, didn't it? So, tell me what the domain of this function is. From where to where? Look at this graph and tell me what the domain of this function that you see the graph of is. 0 to infinity, yes. What is the range of this function? Yeah, somebody said it. It's what? All real numbers. So from -infinity to infinity. Is it continuous or not continuous? In other words, does it have any kind of discontinuity?
Do we need to write -infinity to infinity, or can we just call it?
You could put double bar r if you want to, or write all real numbers, yes. Now, is it continuous, yes or no? Yes, it is continuous. That test is, can I start my pencil here and keep on going either way? Yes, I can. No breaks, no holes, right? Is it symmetrical? No, it's not symmetrical. Remember, symmetrical means it's the same on either side of the x-axis or the either side of the y-axis, right? It's not, is it? So it is not symmetrical. Is it bounded? Top or bottom, right? Is it bounded top or bottom? Can't be if it's all real numbers, can it? So it is not bounded, or we could say unbounded. Are there any asymptotes? There's a dashed line on this graph. There is an asymptote. What kind of asymptote? Horizontal or vertical? So there is a vertical asymptote at where? What equals 0? Which axis does it cross? Yeah. That's how you always tell which one it is. It's the letter, it's the variable of the one axis it crosses, okay? All right. Now, are there any extrema? No, there's no maxes or mins, are there? Last but not least, the limit of f of x as x approaches -infinity. It has to have a maximum or a minimum. It doesn't, does it? It doesn't peak or doesn't have a peak or a valley. Yeah. What is the limit as x approaches negative infinity? What is this thing doing as it's going to the right? What's the lowest x value it gets? 0, doesn't it? It runs into that vertical asymptote, so the answer is 0, isn't it? End behavior, right? Is it 0? Really? Here's the problem. Is it going to negative infinity? See, this is where people screw up. You're like, remember we talked about this. This thing is going to negative infinity, isn't it? But what's the lowest x value it gets? So it never goes, so it says x goes to 0. It goes to negative infinity. So now the other part of that statement is the limit of f of x as x approaches what? Guys, have you ever noticed something? I want you to notice something. Notice this domain value is here, and this domain value is here. Did you ever notice that parallel? For end behavior, whatever your domain values are, the front, top, and bottom would be here and here. So now, what does it go to? And guys, I want to point something else out to you. Have you ever noticed that this is this, and this is that? Huh. Those statements always match the domain. Look, those always match your end behavior statements. This goes together, that goes together. If you've never noticed that before, notice it now and you'll never get them wrong again. If you get the domain and the range right, you'll always get those two statements right. Okay? This x goes with this. Look, this goes with that. And this guy goes with this.
Oh my god.
Ta-da! It's always been that way. Now, you know it now. Describe how to transform the graph into the graph of the given function. So now we need to do our transformations. What transformation is this? Tell me what that transformation is, guys. Left 2. All right. So this guy is normally at 1, isn't it? So if we go left 2 spaces, where does that put it? It puts it here at -1, doesn't it? Yes? So it's going to pass through -1 and go. Isn't that what natural log function looks like? Now, I want you to remember what the initial graph looked like. If this was at 1, this was x equals what? 0? So it was 1 space behind, wasn't it? So if this is now at -1, where's the vertical asymptote going to be? At -2. It's going to be 1 space behind it, isn't it? So this is x equals -2. So the vertical asymptote is always going to be 1 space behind where it crosses the x-axis. Now, we got to rewrite this guy. This is natural log of -x plus 3, correct? Which is this. Natural log of -x minus 3. And yes, you have to pull the negative out. You got to get it in the right form. So what is this transformation of -3? It is right 3, isn't it? And what is this transformation? It's a flip across what? The y-axis, isn't it? Okay, we flip first before we move. So I want you to think about what that's going to look like. All right? So I'm going to draw it in stages. We know that it's normally at 1. If we flip this across the y-axis, normally it does this, doesn't it? Yes? If we flip it across the y-axis, instead of being at 1, where's it going to be? A -1, right? Would you agree? And instead of going this way, what's it going to do? It's going to go the other way, isn't it? So now instead it's going to go this way, isn't it? So this is no longer the case. Now, we flipped it, didn't we? So now we got to move it 3 spaces to the right. So if we move this whole thing 3 spaces to the right, we go from -1 to 0, from 0 to 1, and then we go to where? 2. So this thing is going to go where? This way and down, isn't it? Now, once we get that, guess what we can do? We can erase all the rest of these silly ones that we're just trying to figure out where it's at, aren't we? Now, where is the vertical asymptote going to be? Yes, very good. It's 1 space away, isn't it? So it's going to be at x equals 3.
Wait, so why'd you put that one thing down?
Vertical asymptote. Remember, it always has a vertical asymptote, doesn't it? Like 1 space behind where it curves down. So in this case, 1 space behind where it curves down is going to be in front of it, isn't it? Now, 3 log base x. Does this one shift left or right or up or down? Doesn't, does it? So where is it going to pass through? It's going to pass through 1, isn't it? Yes? It's going to pass through 1, but what does this do? This is a what? Vertical what? It's going to be 3 times taller, isn't it? Would you agree? So we know it's still going to pass through this point right here, isn't it? But it's going to grow what? 3 times faster, isn't it? So instead of going over just a little bit, it's going to go up faster, isn't it? So it's going to grow up faster, much faster. So it's going to look like that, isn't it? Where's the vertical asymptote going to be at for this one? Look at where it's curved and go 1 space, either before or after that. Which way? Backwards this time, right? So it's going to be at 0. So we have a vertical asymptote at x equals 0 and a vertical stretch of 3. All right, so now, what does this do? That is a big number. So what kind of transformation is that? Is it flipping you out because it's first? Rewrite it. Couldn't we rewrite this as log x plus 1? Now, can you tell what it is? It's a big number, so it's a vertical move. So where's it going? Vertical move, if it's added, is going to be either what? Up or down, isn't it? So which way is this one going, up or down? So this is up 1. Now normally this thing goes through 1, 0, doesn't it? But what are we saying? This has to go where? Up 1 from there. So if it's not at 1, 0, if we go up 1, where is it going to be? at 1, 1. So it's going to do this and then do this, isn't it? Where's my vertical asymptote going to be? Y'all can do this. Okay? You can graph these. I promise. You just have to think about what the transformation's telling you. Notice I started every time at this 1, 0 mark, didn't I? If it moves left or right, the asymptote moves left or right. If it moves up or down, did the asymptote move? No. If it stretched up or down, did the asymptote move? No. The only time the asymptote moved was when? When we had a number inside. That's when the asymptote moved. And it moved the same amount as the move was. Left or right? If it went right 3, normally it's at 0. What's 0 plus 3? And look where the vertical asymptote ended up. If this is left 2, wouldn't that be a minus 2? What's 0 minus 2? And that's where the asymptote ended up. You see the parallels? If you see the parallels and you can put the asymptote in, you can figure out where it passes through because it's always one space next to that, isn't it? So if you can move the asymptote, you can figure out where it crosses and draw it in. All right? Okay, guys. That's it for today's lesson. You have 8 minutes left. I want you to do that warm-up that we were talking about. Do those questions, as many as you can between now and then. You can use your homework. You can work together, but I want you to put your name on them, do them, and turn them in this basket before you leave. Let's see what you got.